Let's go to Lico 333, largest BST subtree. So to give us a tree node root and ask what is the largest BST subtree. So firstly, define the binary search tree, right? So you need to, the left subtree value are strictly less than the value of their parents, and the right subtree are greater than the value of their parents. And what is the largest means that she has the largest number of nodes. So the things that we want to do divide and conquer, right? So for example, if this one we already calculated on its left, if a tree, its left child, it is a BST tree, right? And then and we find its largest value and also the smallest value and also the largest count. We need to return three counts, right? And so if we, for its left, it's a binary search tree. We have three values, and on its right, we have min, max, and the max counts, right? Max counts. So if left is a binary search tree and the right is a binary search tree, and also the for its left child, the maximal value is smaller than root dot value, and also the right tree, the minimal value is greater than the root value. So we have candidate from this one and this one, and also the whole tree is a binary search tree. So that will um, be be the whole size, right? So so in that case, we may need a lot of variables. So for example, mean value of the left tree, max value of the of a tree, or size of a tree, or we have a flag. Is it binary search tree? Um, in a postulate, the largest binary search tree counts, right? One, two, three, four, five. That need five variables. Actually, the code is not that good, right? So what we're thinking about is that we need some way to simplify that. That we just return three variables: the minimal value of a tree, and the maximal value of a tree, and also the largest counts of this tree, right? So, so that means that we set if this tree is a null, this one set a maximal value, and max set this as a mean integer mean, and this one set as zero. This is a termination condition, right? And also, we want to check um, if if a node dot value is smaller is greater than its left child tree's max and smaller than the right child tree's mean, right? And also the left child is a binary search tree and the right child is a binary search tree. Then we can have um, the the um, the result actually result the third variable, right, equals left result 2 plus right result 2 plus 1, right? Because because the things that we can make sure this one is a binary search tree. That this one is a binary search tree. So we know this is a binary search tree. So the LR2 will be its size, right? And right 2 will be this size, so plus 1, right? We don't need to have max. And if this condition does not satisfy, we can set set the result to be the smaller to be integer minimal, and also the large value to be integer maximal, right? So and also the result of the maximal will be max between these two, right? In this case, because for this tree, the smallest is already integer minimal, and the maximal will be integer maximal, right? So if we pass it back to some root again, it will never form any BS tree anymore, right? Because this max is already integer max. It's never being smaller, this root dot value. And the same thing on the right, if this is already smaller, integer minimal, right? So it will never be greater. So we just use three variables for this. So let's write code for this. So we'll see for this one, we need a DFS with the UI conquer the tree node root. Let's say node. So what we want is if a node equals null, we just return new integer dot max value and integer dot mean value, right? So this will be initial, and also the count is zero, right? So we return three variables. So zero will be mean value for this tree. One will be the max value for this tree, and two is max sub BST size. Okay. So we iterate these three variables, right? And let's have a left result equals DFS node dot left. And also int right result was DFS node dot right. So we'll say if we have node dot value is greater than left result one, the largest value of the left tree, and node dot value is smaller than right result zero, the smallest of the right child, right? Then we are return new int. So let's have this one to be mass dot mean, left result zero, and node dot value, right? So why we need a mass dot mean? Because it's possible its left child is a null, right? So if it is null, then for this tree, the minimum value will be the root dot value, right? Not the integer max value, right? So on the other, on the max value, we also need the max dot max, right, one, and node dot value. And also, what is the result? We actually, if that means the whole tree is a binary search tree, right? So we don't need to have the left result to originally what we want to should have max dot max, left result to right result to, right? And also the counters of left plus one plus count of right. But the thing is that if we can go to this kind of scenario, that means the left tree is a binary search tree, and the right tree is also a binary search tree, right? So we'll see we can use this one, left result 2 plus right result 2 plus 1, right? So this will always be greater than any of the right side, right? So we can have the size to be this. And else, that means this tree is not a binary search tree. So we can return new um, integer dot min value in the integer dot max value. And we'll have so the count we can just pass in the left choose max count and the right choose count. We just have a max. So left result 2 and the right result 2, right? So if it is not a binary search tree, you see this will become min and this become max. So if we backtrack to its parents, we'll never go back to this condition again, right? So it is never, if for example this is not a binary search tree, and so this will never be added to its parents. So we'll never have any goes to here, right? So it's just passing this result, just the largest account back to its root. So we just need to return DFS root to right. It is ON time complexity, and for space, because it's recursive, it's also ON space complexity. And we can also have Python code for this. Return self.dfs root 2, right? So we can define dfs self.node. This is optional tree node. So this one is going to return three results, right? So left min, right min, and largest count. So list all int. So let's say if a node is none, we return. So for this one, we set as float inf and float minus inf, and this one is 0, right? Then we're going to have left equals self dot dfs node dot left, and right equals self dot dfs node dot right. So we'll say if node dot value, so if left 1, right, is smaller than right 0, right? Then we're going to have we just return so this one we still need a min left 0 and node dot value, and this one should max right 1 and node dot value, and we need to have left 2 plus right 2 plus 1, right? So else we just return, let's say float minus inf and float inf and max left 2 and right 2, right?